Hello everyone, I am Manish Agrawal and you are watching Edupedia World Videos. So continuing with states of matter, today we'll deal with gay-Lussacs law. So we have already seen other gaseous law and gay-Lussacs law is going to be quite similar to them. So it shouldn't be a problem and won't take a lot of time. Alright, so let's start with the basics, what gay-Lussacs law is about. So it is a law which deals with isochoric process. Isochoric processes are processes where volume is kept constant. Okay. So what gay-Lussac did was he kept number of moles again constant. That means the amount of gas inside the container is fixed, as well as the volume of the container is maintained to its initial value. It is not changed, and such processes you have to remember now are called isochoric processes. Alright, so gay-Lussac's law is just a mathematical representation of isochoric process for us. Okay, so starting with our ideal gas equation, PV is equal to nRT. Alright, so N and R are constant here, as well as volume is constant, while pressure and temperature are allowed to change. Okay, so this gives us, from simple mathematical rearrangement, that pressure is equal to nR by V into T, where nR by V can be taken as one single constant, say K. Alright, so that is P is equal to KT. So this allows us to give you gay-Lussac's law in its simple form, that pressure is directly proportional to temperature. This means if in your container you want to increase the pressure without changing the volume of your container, then one thing to do is simply increase the temperature, that is to heat up the container. Okay, so this is what happens in a pressure cooker. Okay, you are maintaining the volume of your container, but you heat up the pressure cooker, as a result of which the pressure inside the cooker builds up. Okay, that is, it keeps on increasing as long as heat is provided to the system, and vice versa. If you decrease the pressure somehow, that is, if you have, say, a lid over here, so this lid will allow the gas inside the container to escape out, okay, or some gas to come in. Let's assume that number of moles of the gas is maintained inside the container, okay, such that pressure is changed. Okay, pressure is changed, but number of moles are in effect maintained. So reducing the pressure will automatically decrease the temperature inside your container. Okay, so this is what pressure directly proportional to temperature means. Another way of looking at gay-Lussac's law is that, okay, P by T is equal to your constant K. That means if initially my pressure was P1 and temperature was T1, and now I decide to change my pressure to value P2, okay, then temperature will automatically adjust itself to a new value T2, such that the ratio is still the same as initial K. Okay, and we know that value of K here is nR by V. Alright, so from this equation 1 and 2 we get that P1 by T1 is equal to P2 by T2. Alright, so this is another form of your gay-Lussac's law. Okay, and this is the form which might generally be helpful for you in numerical questions. So that's it. Now coming to the graphical representation of gay-Lussac's law, we know that here P is equal to K into T. Okay, so let's plot P on our y-axis and temperature on x-axis. So comparing this to the equation of a straight line, y is equal to mx plus c, we get that c, that is the intercept on y-axis, is 0, and m, that is the slope, is equal to k. Okay, so since intercept is 0, the graph will have a straight line passing through origin, and slope m, which is basically tan theta, is equal to k, which is basically nR by V. Alright, so your graph will look something like this. Okay, so let's focus on only one single straight line, say that belonging to V1. Let's forget about the rest of the three straight lines. So pressure in bars is in y-axis. Once again, pressure can be in any unit of your choice. Okay, it can be in atm, pascal, torr, anything, but temperature on x-axis must always be in Kelvin. Okay, over here for the equation to pass through origin, it must be in Kelvin. So for a given container of volume V1, the graph will look like this straight line, the first straight line. Okay, once again here the line is dotted towards the origin and not actually connected directly to the origin, that is, it is extrapolated, because we cannot actually have pressure and temperature as zero. Okay, we are not dealing with gases or systems at absolute zero. Okay, so from here it is quite clear that this is an isochoric process where volume is maintained. So such graphs where volume is constant are called isochores. Alright, so the process is called isochoric and the graph is called isochore. And since tan theta is equal to nr by v, I can say that slope of my line is inversely proportional to volume. Okay, so that is to say, now if I take the same amount of gas and allow the container to change its volume to V2. Okay, and now at V2 I've again fixed the volume, that is, now I'm not allowing the container to change the volume from V2. So the graph will be the second straight line. Okay, the pressure versus temperature graph will change to second straight line. Now this again is an isochore, and then if I change the volume of container to V3 and again try and plot the graph for gay-Lussac's law, that is between pressure and temperature, the graph will be the third straight line. Okay, and in order to find the relation between these four volumes V1, V2, V3 and V4, we can simply look at the slopes of these lines starting from theta 4 towards theta 1. Okay, so the greatest slope or greatest theta is for V1 and the least is for V4, and we know that slope is inversely proportional to volume over here. That means the greatest theta will represent least volume, so V1 will be least and V4 will have maximum value. That is why the relation is V1 less than V2 less than V3, which is less than V4. Okay, so even the graphical representation is quite similar to Charles' law, except where we had pressure, now where we had pressure, now we have volume, and where we had volume, now we have pressure. Alright, so let's take a quick look at a numerical example and get over with this law. So in this question we have an ideal gas present inside a container, okay, whose pressure is 30 atm. So the pressure inside the container right now has been given as 30 atm because it is the pressure of ideal gas. We don't care about pressure outside the container. Okay. And the temperature of the gas is now changed from 27 to 37 degrees centigrade. That is to say, when initial pressure was 30 atm, the temperature, say T1, was 27 degrees centigrade. Okay, since temperature must be in Kelvin, let's change it right here. 27 degrees centigrade will be 300 Kelvin. Okay, and if temperature is changed to T2, it is asking us what might have been the new pressure in order to change the temperature. So the new temperature is 37 degrees centigrade. Changing it to Kelvin, by addition of 273 we get temperature in Kelvin as 310 Kelvin. Okay, so it is asking you how much pressure must have been increased so that temperature increased by 10 Kelvin. Okay, so directly using gay-Lussac's law, which says that ratio of pressure and temperature in an isochoric process is constant. So P1 by T1 is equal to P2 by T2. That means 30 divided by 300 Kelvin is going to be equal to P2 divided by 310 Kelvin. Okay, so from here it's quite clear. Okay, from here it's quite clear that P2 or the final pressure of the container must be 31 atm. That is, we had to increase the pressure by 1 atmosphere in order to increase the temperature by 10 Kelvin. Okay, so a very straightforward numerical, and now you just need to solve some more questions by yourselves on Gay-Lussacs law, and you will find that they are all pretty simple actually. Okay, you rarely face problem in those questions. You just need to interpret the question in a step-by-step manner, okay, so as to arrive at the final answer. So until next time, and once again thanks for watching Edupedia World videos.